Welcome to another deep dive. Today's mission is designed specifically for you to explore, well, the absolute bleeding edge of generative AI research.
Yeah, we're getting to some pretty mind-bending territory today.
We really are. And to start off, we usually think about medical diagnoses as the gold standard for identifying a problem, right? Like you break your arm, the X-ray machine snaps a picture, and it shows a clear, jagged white line.
Right, exactly. The doctor points to it, and you know exactly what went wrong.
Yeah, exactly. But imagine stepping into the world of generative AI. In this world, your diagnostic X-ray machine seems to work perfectly. It hums along, takes a scan, and produces this incredibly high-resolution image.
Which is great until you look closely.
Right, except it confidently draws in a jagged bone fracture that simply isn't in your arm at all. The machine just, fabricated it out of thin air, and it presents it to you as absolute reality.
And that false bone fracture is basically the perfect visualization of hallucination. We are looking at a diagnostic landscape for AI flaws that is, honestly, incredibly murky right now.
It's a huge problem.
It is. Determining why these wildly advanced multi-billion parameter systems still just confidently make things up is the most pressing issue in the field.
So to pull back the curtain on this, we are unpacking a May 2026 preprint paper. This is by researchers at the Tata Institute of Fundamental Research, and it's titled Innovation, an almost characterization of hallucination.
Right. And it's a fascinating read.
Okay, let's unpack this, because framing innovation as a flaw feels completely counterintuitive. I mean, we treat innovation as the ultimate compliment for a human mind, right?
Absolutely.
You call someone innovative and you're comparing them to historical giants. Yet our goal today is to understand why this exact trait, this ability to generate something novel, is the mathematical smoking gun for an AI's tendency to lie to you.
The paper entirely shifts the blame for this problem. Because for years, the assumption has been that AI hallucinations are the result of complex statistical errors.
Like bad data or something.
Yeah, exactly. Like maybe the training data was too messy, or the neural weights didn't calibrate properly, or there was some glitch deep in the attention mechanism.
Right.
But the authors argue the cause isn't a glitch at all. The root cause is a simple, almost human-sounding behavioral trait. But to really grasp how they arrived at this, we first need to establish the abstract environment, the world, basically, that these language models actually operate within.
That makes sense. I mean, we can't figure out why a machine is lying to us until we understand what the concept of truth even means to a mathematical model.
Exactly.
And I know the authors lean heavily on a pivotal 2024 framework by two researchers named Kalai and Vimpala to set up that world.
Yes, the Kalai-Vimpala framework is the foundation for this whole line of thinking. What those two researchers did was abstract away all the messy physical architecture of neural networks.
So no hardware talk.
Right. They ignored the hardware, the layers, the specific algorithms, and just looked at language models purely through the lens of probability. In their framework, there's a massive meta-distribution of all the possible document distributions that could ever exist.
Okay.
And they simply called it the world. And from that infinite world, one specific true document distribution is drawn. The paper refers to this mathematically as dollars.
Let me stop you there, because the definition of a fact in this mathematical world is totally divorced from how we use the word in everyday life.
Oh, completely.
For Kalai and Vimpala, a fact has nothing to do with universal semantic truth. It's not about, gravity pulling objects downward or water being wet. A fact is strictly defined as any statement that exists within that true document distribution, dollar.
Yeah, the math doesn't care about reality.
Right.
If a statement is present in the distribution, the model considers it a fact.
Wow.
And if the statement is entirely absent for the distribution, generating it is considered a hallucination. There is zero semantic notion of truth.
So, if I build a closed ecosystem, right, and I train an AI exclusively on a multi-terabyte data set of Lord of the Rings and high fantasy novels.
Okay, I see where you're going with this.
Then the statement, dragons breathe fire, is a hard, indisputable fact in that model's world. And the statement, taxes are due in April, is a complete hallucination because the concept of the IRS just doesn't exist in Middle-earth.
Precisely. The model only knows the boundaries of the universe you feed it. And building on that concept, Kalai and Vimpala introduced a critical variable called missing mass.
Missing mass.
Right. Imagine you generate a massive training corpus by repeatedly sampling documents from that true distribution. No matter how many times you pull a document, you're eventually going to miss certain statements.
Just by chance.
Exactly. The missing mass is the probability mass of all the valid statements that genuinely exist in the true distribution, but simply by sheer chance never made it into your specific training data set.
That missing mass has to be enormous in practice, right? Like, even if you scrape the entire internet, Wikipedia, Reddit, digital libraries, you are only capturing a fraction of the overarching human distribution.
Right, it's just a tiny slice.
The highly specific details at a local chess tournament in 1923 might be a fact in the world's distribution, but it might not be written down in your digital training text, so it becomes missing mass.
Yep. The universe of possible valid statements is functionally infinite, and your data set, no matter how many petabytes of hard drives it fills, is rigidly finite.
That makes sense.
So the next step in their 2024 framework was defining calibration. In a probabilistic sense, a model is considered perfectly calibrated when the distribution of the words it outputs perfectly matches the true document distribution.
Reading it understands the data.
Yeah, it essentially internalizes the underlying reality of its training data flawlessly.
A perfectly calibrated model sounds like the absolute holy grail for a developer. It understands the underlying distribution without any statistical errors. But this is exactly where Kalai and Vimpala dropped their massive catch in 2024, didn't they?
They really did.
A perfectly calibrated model doesn't solve the problem at all.
Far from it, actually. Their main mathematical proof demonstrated that a perfectly calibrated model that encounters significant missing mass is practically guaranteed to hallucinate.
Let's ground this in a real-world dynamic. Think of a medical student who has spent years perfectly memorizing a massive textbook.
Okay.
That student represents our perfectly calibrated model. They know the precise tone, the vocabulary, the way the authors structure a diagnosis. But let's say the final exam includes a dozen questions pulled from Chapter 5, and unbeknownst to the student, Chapter 5 was accidentally ripped out of their specific copy of the book before they started studying.
Ah, the missing mass.
Exactly. That ripped out chapter is our missing mass. When the student sits down for the test and encounters those questions, they are absolutely going to hallucinate an answer.
They have to.
Yeah, they will use the perfect medical tone and the right vocabulary to invent a highly plausible sounding disease because they are perfectly calibrated to the style of the book, but they lack the actual data.
Right, the student has no choice but to guess. And because their style is so accurate, the guess sounds incredibly convincing. The Kalai-Vimpala existence result formalize this dynamic mathematically.
Right.
They prove that calibration combined with significant missing mass inevitably results in hallucination.
Wait, if the problem is just missing mass in the textbook, doesn't that mean if we just give the AI a massive enough corpus of training data, the hallucinations will eventually disappear? Like, just buy more textbooks, right?
You'd think so. I mean, the entire multi-billion-dollar trajectory of the tech industry is essentially betting on that exact assumption. The belief is that scale is all you need.
Just feed the model more of the internet.
Exactly. The assumption is the missing mass problem will resolve itself. But the 2026 paper we're looking at directly confronts this assumption.
And they do it by pointing out that the missing data itself isn't the active trigger, is it? The model's reaction to the missing data is the problem.
Yes.
This brings us to their central definition of innovation. If I am tracking the math in the paper correctly, innovation doesn't mean writing a groundbreaking symphony or inventing a new piece of hardware.
Not at all.
It simply means the model assigns a probability greater than 0 to a sequence of words that was completely absent from its training corpus.
The definition is brutally stark. It produces something mathematically unseen. It reaches beyond the literal sequence of tokens it was explicitly given.
It's generating a combination of words that it has literally never seen stitched together in that exact way before.
Right. And the moment it does that, it crosses the threshold into innovation. The authors use this to completely rewrite the Kalai and Vimpala logical chain. Well, the 2024 assumption was that calibration plus missing mass directly implies hallucination. But this new paper proved there is a crucial middle step. Calibration plus missing mass forces the model into innovation.
Oh, wow.
And it is the active innovation that fundamentally guarantees hallucination.
So the paper calls this an almost characterization, meaning they are effectively the same thing. If a model is hallucinating, it must be innovating by definition. You can't produce a false unseen statement without first producing an unseen statement.
Exactly.
But the reverse is the real gut punch for the AI industry. If the model innovates, the math states it will hallucinate with incredibly high probability. They are inextricably linked.
They're two sides of the same coin.
Here's where it gets really interesting, though. To stop a model from hallucinating, you essentially have to force it to never innovate. It has to act as a strict, unthinking parrot. It can only regurgitate the exact phrasing it digested. But the entire utility of a large language model, the reason we use it to summarize documents, write code, or draft emails, is because we want it to synthesize and generate novel text. We want it to think outside the box.
That's the whole selling point.
Exactly. The paradox here is that the very capability that makes the tool valuable is the exact mathematical trigger that causes it to fabricate information.
The paradox is inescapable.
Mm.
The utility and the fatal flaw are drawn from the exact same probabilistic well.
So the natural developer pushback here would be about moderation. If innovation is the trigger, can we just turn down the dial? Allow the model to innovate just a little bit, give it a tiny amount of creative leeway so we get the usefulness, but keep the hallucinations at a manageable baseline.
That's the logical next question. And the paper tackles that exact mitigation strategy,
Right.
and the math they use to dismantle it is arguably the most important contribution to the research.
Because it doesn't work.
No, it doesn't. They prove that innovation is an inescapable trap, regardless of how far you try to dial it down. They do this by establishing two mathematical lower bounds on the hallucination rate. One is a Markov-style bound, and the other is a high-confidence bound.
Okay, whenever we hit terms like Markov bounds, we run the risk of losing the forest for the trees. Let's translate these bounds for the listener.
Fair enough.
In standard statistics, a Markov bound is essentially a rule that limits how often extreme deviations can happen based on your overall average. Like if the average height of your group of people is 5 feet, a Markov bound proves it is mathematically impossible for more than half the room to be 10 feet tall.
That's a great way to put it. And applying that statistical rule to an AI model reveals a harsh reality. The Markov-style bound in the paper proves that if your model has a high average rate of innovation, the hallucination rate cannot mathematically hide near zero.
It pulls it up.
Yes. The bound enforces a strict ceiling on how lucky the model can get. It guarantees that the errors will drag the average hallucination rate up, along with the innovation rate.
And the high confidence bound seems even more problematic for developers. It shows that even if the language model calculates a 99% internal certainty that its novel guess is correct, like even if it is highly confident, the mere fact that it is an unseen innovation triggers a strict mathematical floor for hallucination.
Exactly.
It doesn't matter how large the training corpus, denoted as a nuller, actually is.
Right. The corpus size nullers is rendered totally irrelevant. Previous industry theories held on to the hope that as non approached infinity, as you scraped more and more data, the hallucination rate would naturally decay towards zero.
But that's not true.
No. They prove that as long as the innovation rate remains positive, the hallucination rate will persist and scale with it, completely independent of how massive dollar gets.
That completely vaporizes the brute force data strategy. You can't just buy a bigger hard drive and solve hallucination.
The scale of the data cannot fix a fundamental behavioral mechanism. The paper outlines the underlying architecture of this trap by showing that every model attempting to guess an unseen statement is forced into choosing between two failing strategies.
What are they?
The model can either spread its probabilistic guesses broadly across many different unseen statements, a strategy they call scattering, or it can concentrate its probability sharply on one specific unseen statement, which they call spiking.
Imagine playing darts blindfolded. You know the dartboard is out there somewhere on a massive blank wall in front of you. You have two ways to play. You can grab a massive handful of darts and just chuck them wildly in every possible direction all at once, hoping one finds the board.
That's the scatter strategy.
Right. Or you can take one single dart, visualize where you think the board is in the dark, and throw it really hard at that specific spot. That's the spike strategy.
Visualizing it that way makes the model's dilemma incredibly clear. The paper relies on two fundamental assumptions about the AI's mathematical world to explain why both dart strategies fail.
Okay, what's the first one?
The first assumption is case sparsity. This implies that true facts are astonishingly rare compared to the nearly infinite number of false ways you can combine words. The bullseye you are aiming at is microscopic, and the empty wall surrounding it stretches on for miles.
So if I am using the scatter strategy, throwing handfuls of darts blindly into the dark, the sheer vastness of the empty wall means almost all of my darts are going to miss the board entirely.
Yes. If the model spreads its probability broadly, the sparsity of truth defeats it. The vast majority of those unseen statements are mathematically false, so the scatter strategy guarantees a high volume of hallucinations.
So realizing the scatter fails, the model switches to the spike strategy. It takes one dart and throws it confidently.
And the spike strategy runs face first into the second assumption, which is regular facts. This means that once the model steps outside its observed training data, it loses all reliable signal.
It's blind.
It has no internal mechanism to distinguish between a genuinely rare true statement and a common false statement. It is truly blindfolded. So when it concentrates sharply and spikes its probability on one guess, the regularity defeats it. It has no factual basis to aim, meaning the spike almost certainly lands on the empty wall.
The trap is absolute. Because the bullseyes are so rare and the empty wall of false combinations is so massive, you are going to put holes in the wall no matter what strategy you use.
Exactly.
Whether the AI scatters its guesses or spikes its confidence, if it throws a dart while blindfolded, if it attempts to innovate beyond its data, it is mathematically destined to hallucinate.
The mathematical certainty is what makes the paper so compelling. The only possible way to avoid putting a hole in the wall is to refuse to throw the dart. The model must maintain an innovation rate of absolute zero.
Moving from the theoretical math to the real world poses a massive challenge, though. We know companies like OpenAI, Google, and Anthropic treat their multi-terabyte training data sets as highly classified trade secrets.
Oh, heavily guarded.
Yeah, no independent researcher has access to the exact text GPT-4 was trained on. So how did the Tata Institute researchers actually prove this tight correlation between innovation and hallucination empirically if they couldn't see the underlying data?
Well, they had to engineer their own controlled universe from scratch.
Right.
They built they call it a toy setting, where they possessed godlike access to both the model's architecture and the entirety of its training data.
Clever.
They utilized a public data set consisting of roughly 3,000 customer reviews, just standard restaurant and product evaluations, and they strictly capped each review at a maximum of 20 words.
Keeping the universe small enough to perfectly track every single variable.
Exactly, a completely closed system.
Okay.
Within that system, they trained simple n-gram models on the review data. N-gram models are much more rudimentary than modern neural networks. They operate by simply predicting the next word in a sequence based entirely on the previous n number of words.
Right.
The researchers tested models using orders 2 through 7.
To clarify how an enneagram works for anyone unfamiliar, an order 2 model just looks at the single previous word to guess the next one. An order 7 model looks at the last 6 words in a row to calculate the probability of the 7th word. It's a very straightforward statistical chain.
And because the researchers possessed the full data set, tracking the exact innovation rate was trivial. They simply took the sentences the Enneagram models generated and cross-referenced them against the training data.
Just a direct comparison.
Yeah. If a generated 20-word review did not exist anywhere in the 3,000 source reviews, it was definitively categorized as an innovation.
The tricky part is judging the hallucination rate, though. In their defined framework, a hallucination doesn't mean the review is factually inaccurate about a real-world restaurant, right?
Right, because there's no real-world grounding.
It just means the generated text wouldn't logically belong in the overarching distribution of actual human reviews. Like, it sounds fake or nonsensical. How do you reliably measure that?
The evaluation process they set up was rigorous. First, they employed human evaluators to manually review about 900 of the generated statements, asking them a simple binary question.
Yeah.
Could this pass as a real human-written review?
Okay.
But they didn't rely solely on human intuition. They took the Enneagram outputs and fed them into 4 of the most powerful foundation models available, acting as judges. So we're talking Gemini 3 Flash, Claude Sonnet 4.6, DeepSeek v3.2, and GPT 5.4.
Using massive trillion-parameter LLMs to fact-check the output of tiny statistical models. That highlights a massive bottleneck in the industry right now, honestly. Fact-checking AI output with other AIs is incredibly computationally expensive.
It's turtles all the way down.
It really is. It requires massive processing power to prompt a model like GPT 5.4 just to verify if another model is telling the truth.
The computational overhead of using LLMs as judges is astronomical, which is why finding a cheaper metric is so crucial. When they ran the outputs through these judges, the resulting charts were striking.
What did they find?
Across the board, whether the judge was a human being or GPT 5.4, the plotted innovation rate tracked the hallucination rate almost perfectly. As the simple Enneagram models attempted to innovate more often, the amount of hallucinations flagged by the judges rose in exact lockstep.
I can already hear developers finding a flaw in this methodology, though. Language is inherently flexible. If the training data contains the phrase, "the food was good," and then Enneagram model outputs, "the food was great," it has technically generated an unseen sequence.
That's true.
Under a strict literal definition, it innovated. But practically speaking, those two sentences convey the exact same semantic meaning. If the researchers relied on strict word-for-word matching, wouldn't they just be punishing the model for basic paraphrasing?
The authors recognize that literal matching is far too brittle for evaluating natural language, so they introduced a mechanism to test semantic innovation. They didn't just look for exact string matches, they looked for novel concepts.
So they needed a way to measure whether an idea was genuinely new, rather than just a synonym.
Yes, and they utilized an embedding model, specifically the all-middle LM L6v2 sentence transformer. What this does is convert entire sentences into mathematical vectors.
Imagine taking a massive dictionary and mapping every single concept into a three-dimensional physical space. Words with similar meanings live in the same neighborhood.
Exactly.
Like king and queen live on the same street, while apple, the fruit, lives in a totally different zip code than Apple, the tech company.
Now take that 3D map and expand it into hundreds of mathematical dimensions. The transformer maps the sentence's meaning to a specific coordinate in that high-dimensional space. The researchers then measured the cosine similarity between the vector of the generated review and the vectors of the training data.
Okay.
Cosine similarity simply measures the angle between those coordinates. A score of 1.0 means they're identical. The researchers set a threshold of 0.95. If the similarity fell below 0.95, it meant the model had moved far enough away from the original neighborhood of concepts that it counted as a true semantic innovation.
That's brilliant. It allows the model to paraphrase freely without being mathematically penalized, as long as it stays in the same conceptual zip code. When they ran the charts again using this semantic flexibility, did the correlation hold up?
The correlation remained incredibly robust. Even when giving the models the freedom to paraphrase, the rate at which they generated genuinely novel semantic concepts perfectly tracked the rate at which they produced logical hallucinations.
So what does this all mean for the big tech companies? Because I have to play devil's advocate regarding the scale here. The researchers proved this connection on an Enneagram model trained on 3,000 Yelp reviews. We are trying to apply this logic to models like GPT-5.4, which are trained on trillions of tokens with unimaginably complex attention mechanisms.
It's a fair point.
The difference in scale isn't just large, it's astronomical. Does a simple Enneagram model's toy setting really apply to a frontier model? Can we actually trust that?
The scale difference is the most valid critique of the empirical data. The authors themselves readily acknowledge that the core probabilistic assumptions of the Kalev-Impala framework are almost certainly violated when you scale up to real-world, complex semantic tasks.
Right.
The toy setting is a simplified abstraction. However, the theoretical link they've exposed offers a profound practical utility for the developers building those massive models.
Because it offers them a proxy metric. As we discussed earlier, directly measuring hallucination during the training of a frontier model is practically impossible.
It really is.
You can't automatically verify if a highly complex generated output is factually true without constantly querying external databases or running secondary AI judges, which cost millions of dollars in compute.
But measuring the innovation rate is computationally cheap and incredibly easy. A developer can quickly calculate how often a model's outputs deviate from the vector embeddings of its training data. If the tight mathematical correlation holds true even partially at scale, trainers just found a reliable new speedometer for hallucination. They don't need to hunt for the lies directly, they just monitor how fast the model is trying to innovate.
It's a completely new paradigm for evaluating models before they are ever released to the public. If we zoom out and look at the whole picture, the deep dive into this paper fundamentally reframes our understanding of AI failure.
It really changes the conversation.
The simplest, most irreducible condition for an AI hallucination isn't a complex miscalibration or poor data hygiene or a rogue algorithm. It is the simple mathematical act of a system trying to reach beyond the boundaries of what it explicitly knows. The innovation rate is the direct predictor of the hallucination rate.
That's the core takeaway.
You mathematically cannot have one without the other, and no amount of massive internet scraping will solve the problem as long as the model is still attempting to guess at the unseen.
The scatter versus spike trap ensures that as long as the model is blindfolded and throwing darts, it will inevitably hit the empty wall of fabrication.
It really forces you to reconsider what we are actually asking these machines to do. The paper's discussion section features a concept that is worth lingering on. The authors propose the idea that hallucination is essentially just innovation in the absence of semantic feedback.
Framing it as an absence of feedback is a critical distinction.
If you look at how human cognition develops, you see this exact pattern. I have a toddler, and watching him learn language is fascinating. He constantly invents fake words. He applies grammatical rules with absolute unwavering confidence, even when they are completely wrong.
Like saying I runned instead of I ran.
Exactly. He makes up wild theories about how the physical world works, and he treats them as facts until an adult intervenes and corrects him. That parental correction is the semantic feedback.
Without that external grounding, the toddler would simply continue to confidently hallucinate his reality.
Exactly. The human mind requires that messy, confident, error-prone phase of guessing to eventually achieve true creativity. So it leaves you with a profound question about the nature of the systems we are building. Is hallucination really a bug in artificial intelligence?
That's the million-dollar question.
Or, returning to our diagnostic X-ray machine, is the machine actually showing us exactly what a developing neural architecture is supposed to look like? Is confident hallucination not a disease to be cured, but rather the mandatory, chaotic first step toward genuine, independent digital thought?
When you view hallucination as the necessary precursor to true innovation, the entire landscape of AI development shifts.
It gives you an entirely new way to look at the errors in your next chatbot prompt. Thank you for joining us on another deep dive. We'll see you next time.